Hello, welcome back. The title of this lesson is called Chemical Formulas and Models. So before we get into chemical reactions, we need to spend several lessons on understanding what a chemical formula is, how to write down chemical formulas, and also talk about the different kinds of chemical formulas. And we're going to have to, in order to get a good understanding of this, touch on the different kinds of bonding that we're going to really talk about. When I say the word bonding, I'm saying that two or more atoms come together and they kind of get stuck together, and that process is called bonding. Now, why do elements bond together? How exactly does it happen? All of those details, we're going to answer those questions as best we can, but we have to push some of the details away, right? Because if you try to do too much too soon, then everybody gets lost. So instead, you're just going to have to trust me that things like to bond together, and there's a physical reason for why they like to do this, but there are different flavors to the kinds of bonding, and that's going to lead to different types of combinations of atoms, okay? So we have, in the broadest sense, we have molecules, right? And then we also have ionic compounds. So those two big classes we really have to tackle in the beginning, but keep in mind, even though we're putting a roadmap together and talking about the chemical formulas of both types, as we go further down, we're going to dive into each of these types, molecular and ionic compounds. We're going to dive into those in a lot more detail in subsequent lessons. This is an introduction and an overview. So here we have the periodic table. Now, this is what I wish somebody would have told me at the very beginning. There's basically two broad kinds of bonding that happens between elements. I just mentioned their names. One of them is called a molecule, which also has another word, molecular bonding, right? We also call it covalent bonding. I'm going to write these words down, but they all basically mean the same thing. They form molecules. And those happen when you have elements from the right-hand side of the periodic table bonding together, right? Like carbon dioxide is CO2. So there's a carbon and oxygen there. That's an example of that. Now, when I say from the right-hand side of the periodic table, you got to consider that hydrogen, even though it's on the left, hydrogen can either gain electrons or lose electrons. And so it's a little bit of an oddball. It's on the left-hand side of the periodic table, so it looks like it's a metal, but actually it's really not a metal, right? So we're considering hydrogen, even though it's on the left, as part of this grouping. So when you bond things from the right-hand side of the periodic table together, and we can include hydrogen in that list, even though it's really not on the right-hand side, then we have molecules, we have molecular compounds, okay? Now I'm going to write that down, but before I do write it down, the other class is if you have something from the left-hand side of the periodic table bonding with the right-hand side of the periodic table, we call that an ionic bond. The best example of that is table salt. Sodium chloride is something from the left and something from the right. So basically there's two broad possibilities. Either something from the left is going to combine with something on the right, that's called ionic, or two different things from the right can bond together. And we also include hydrogen in that as being on the right, even though it's physically written on the left. It behaves more like something on the right-hand side of the periodic table, at least in these discussions here. So either left plus right or right plus right. Those are the possibilities, and they do lead to very different outcomes. Now, in the beginning of chemistry, it's very easy to gloss that over and say, I don't care. I just care about how things combine together. I don't care if it's left plus right or whatever. I only care about looking at what forms and looking at the formula and understanding that. But I'm trying to introduce these ideas early on because those two differesces, ionic versus covalent, or ionic versus molecular, same sort of thing, they lead to very, very different situations in the microscopic level. So even though you could kind of ignore it for now, I don't want you to, right? So left plus right, that's one class, or right plus right. Now, in general, we never have two things bonding on the left. With one exception, hydrogen. Again, it's a little weird. Hydrogen is just weird by itself because it's the simplest atom we have. But in general, you don't have, calciums just bonding together or potassiums just bonding together like this. So it's left plus right or right plus right. I keep saying it over and over again because it's important, okay? So let me go ahead and summarize this. So we're going to call, if you have something from the right-hand side of the periodic table and you combine it with something else from the right-hand side of the periodic table, then it forms what we call a molecule, right? A molecule. And another word for that, you might say that it has a molecular formula. might make sense that it's a molecular formula, right? Because it forms a molecule, right? The type of bond that happens when something from the right combines with something from the right is called a covalent bond. Now, your next question is, well, what's a covalent bond? I'm going to tell you right now. A covalent bond is when electrons between the two atoms are shared. Electrons are shared between them, right? Now, we're going to get into all this later because you know that electrons exist around all these atoms, but we've never told you, I've never told you, how they're packed into the outside of the atom. How are they moving around? How are they transferred? How are they shared? We haven't talked about any of it, but I'm just telling you that in general, when two elements or two or more elements from the right-hand side of the periodic table form a molecule, the electrons are not transferred between them, they are shared. And that electron sharing forms a type of bond that we called a covalent bond, okay? Now, what is the best example of this? Or some examples of this. There's many examples, right? But example is oxygen gas. Oxygen does not like to exist as just a single atom by itself. If you go get a bottle of oxygen from the hospital or for mountain climbing or whatever, then it's going to consist of oxygen in there, but the oxygen atoms are going to automatically bond together in pairs. That's why it says O2. This means two atoms of oxygen bonded together. We're going to talk about the details of how that bonding happens, but you know it's a covalent bond because these are two atoms from the right-hand side of the periodic table, two oxygens bonding together. And you also know, because I'm teaching you this now, what type of electron business is happening. Are the electrons being transferred somehow, or are they being shared? Well, we're saying right now that electron sharing is happening. So these two oxygen atoms, they are going to have a force of attraction between them, and they're going to stick together. We call that a covalent bond, and the electrons are being shared. What's another example? Another example is of famous water. Or you might say hydrogen peroxide. Or you might say methane, CH4. There's lots of examples, but notice in all of these cases, it's atoms from the right-hand side. Notice I said hydrogen, even though it's on the left, it counts as though it's on the right-hand side because it behaves more like a gas, more like a non-metal, right? So H2O, H2 and O, those are from the right-hand side. H2O2, again, atoms on the right-hand side. What else do we say? CH4, C, carbon, H4. Again, we're counting hydrogen as being on the right. In all of those cases, they form covalent bonds and the electrons are shared. They're shared between the atoms. Okay, we're going to talk a lot more about why they like to be shared and why is there a force of attraction. We're going to talk a lot about those details later. For now, we have to kind of move on to get the big picture, and then we get into the nitty-gritty details of why. All right? Then we have what happens in the situation. This was when you had an atom on the right combining with one or more atoms from the right. What if you have an atom on the left combining with or bonding with an atom on the right? Remember, I told you can have right plus right or left plus right. You cannot have left plus left. That just doesn't really happen. Or it would be some exotic situation. It is not a common situation. So we don't call these molecules anymore. You know, we don't, a common misnomer, for instance, sodium chloride is the prototype you should have in your mind for a left plus right. We all need to have a prototype in our mind. You know that when you think of a ball, you have a prototype in your mind, probably something you played with when you were a child. Or a bicycle, you have a prototype in your mind what a bicycle looks like. So we have to have a prototype in our mind. A covalent molecule, covalently bonded molecule, the prototype I use is water because it's the most common thing, and it's a covalent bond and it's a water molecule. You know this. For an ionic compound, left plus right on the periodic table, my prototype is table salt, sodium chloride. That I would recommend to be yours because it's something that you see every single day. So it does not form a molecule. A big misnomer is people say see sodium chloride, NaCl, and they think it forms a molecule. It actually doesn't. I'm going to show you the difference right in just a minute between what sodium chloride looks like at the microscopic level compared to a water molecule, and they do look different, completely different actually. So we do write it as NaCl, and it does look like it forms a molecule of one atom of sodium and one atom of chlorine, but it doesn't form a molecule. Instead of saying that it's a molecule, what we do say is we just say it's an ionic compound. Right? And we also say that it's an ionic bond. So there's two types of bonding, right? You have an ionic bond and you have this covalent bond. Covalent bond was when the electrons between the atoms are shared. Well, what happens in the ionic bonds? The electrons are no longer shared, they're transferred. What is the difference between sharing something and transferring something? If you're standing next to me and we share a candy bar, then we hold the candy bar between us and we both start eating it or holding it or whatever, but we're sharing it. But if I transfer the candy bar, I literally take it and I give it to you. It's yours. It's not even in my sphere of influence anymore. I've given it away. An ionic bond happens when electrons are transferred. That means that one atom literally gives an electron to another atom. Now, these atoms don't care about giving or receiving. They don't have feelings, right? Why does it give an electron? It all comes down to the electric force. The electric force is millions of times stronger than gravity, and it dictates all of this stuff. So why do atoms sometimes want to transfer? Because of the electric force. Why do they sometimes prefer to share instead of being transferred? It's all because of the electric force. We're going to get to those details later. I can't talk about it now because there's too many things we haven't learned yet, but it all comes down to how the electric force works. And when the electric force is strong enough, then the electron will be ripped out of one atom and transferred to the other. And when the electric force is shielded and not as strong, they end up becoming shared. Okay, that's, again, a discussion for a future lesson, but that's the basic idea. So if we call this an ionic compound, we call it an ionic bond, we say that electrons are transferred instead of being shared, what is the prototype example of a left plus right type of situation? Sodium chloride. That's what I would use. But just to give you one more so we don't just say this over and over again, you can have potassium chloride. So notice that potassium and sodium are in the same group, group 1 here. So potassium, one atom of it can combine with one atom of chlorine and they're happy partners. And I'm sorry, I may have said potassium. Sodium can combine with chlorine and potassium can also combine with chlorine. Now, and they form in the same ratio, 1-to-1 ratio. So this means one atom of sodium, one atom of chlorine. The ones here are invisible, but they are there. One atom of potassium, one atom of chlorine. So that's how they join up. It is not correct to say this is a molecule. It is not correct to say that this is a molecule. You're going to understand why in a second, but they're not molecules. Molecules are, for instance, this is a water molecule. If you had superhuman vision and could zoom in on a cup of water and then you could see these things swimming around together, they would be free-floating independent units that are bonded together in the ratio of 2 hydrogens and 1 oxygen, right? So this is a methane molecule, right? It's got CH4 is the formula. It is 1 atom of carbon and 1, 2, 3, 4 atoms of hydrogen bonded around the periphery like this, right? Notice the symmetry that the hydrogens are all going out equidistantly and with the same angles spread around there like this. But this is a free-floating molecule. It is literally something that can bump into its neighbor and bounce off and things like this. But that is only happening because it's 2 atoms from the right-hand side of the periodic table. What does sodium chloride look like? I'm going to save that for just a second. We're going to talk about it in just a second. But sodium on the left and chlorine on the right, they do join up, but they don't form a molecule. I'm going to show you what that means in a minute. But before I do, I'm going to remind you of something I taught you in the last lesson when we talked about the periodic table. In general, we said the periodic table has on the right-hand side, this group over here on the right, we call it the noble gases. And what's happening with the atoms that are next in the groups next to the noble gases, they want to try to achieve a electron configuration, which we'll talk about the details later, but they want to have an outer layer of electrons that is the same as the nearest noble gas to wherever it is on the table. So chlorine always wants to gain 1 electron and look like the outermost electron configuration of argon. And it can do that by attracting an additional electron. So chlorine wants to gain 1 electron to look like argon as far as its electrons go. Fluorine also wants to gain 1 electron to look like its nearest noble gas, neon. Oxygen wants to gain not 1, but 2 electrons to look like neon. So everything on the right, you can predict when you're close to the edge like this, you can predict how many electrons it wants to gain in order to look like wherever it's like bromine generally wants to gain 1, iodine generally wants to gain 1. We're going to talk about these things later, but I don't want to hide this from you because it influences so much of what we talk about in chemistry. So these want to gain electrons to look like a noble gas. But over here, sodium, for instance, it doesn't want to gain electrons because it would have to gain a bunch of electrons to get over next to argon. Instead, what it would rather do is lose an electron, and then it would look like the previous noble gas, because notice neon is atomic number 10 with 10 electrons, 10 protons. Sodium is atomic number 11 with 11 protons, 11 electrons. So it's going to be easier from an energy point of view to lose an electron and look like neon. So sodium would like to lose an electron. Potassium would like to lose an electron and look like the outer layer of electrons of argon. Now, I'm using words like it wants to do this, it wants to do that. It doesn't have feelings. Potassium doesn't care. It doesn't have any desires. It wants to lose an electron because of the electric forces involved. Because we're going to learn later that potassium has an outermost electron that's very weakly attached. It's not held very strongly to the outside layer of the atom. And since chlorine wants to gain an electron to look like this, and then sodium has an outermost electron that's very easy to get rid of because it's kind of way, it's like Pluto, it's way at the end. It's very weakly held. If chlorine really wants an electron because of a strong electric force, and let's say sodium really wants to lose an electron because it has a weakly bound electron, what's going to happen? Sodium's going to lose its electron, chlorine is going to attract it strongly, and it's going to get transferred over. So when you have something from the left side of the table reacting with something from the right side of the table, always what's happening is an electron is lost over here and it gets transferred to its partner on the opposite side. That's why sodium chloride is so common in nature. It's filled in the oceans because it's a very, very stable compound. Because chlorine really wants to grab an extra electron and sodium really wants to lose an extra electron, so they partner up and they're happy. Same thing happens with sodium bonding with chlorine. So, or I should say potassium bonding with chlorine, making potassium chloride. Magnesium wants to lose an electron too, but it wants to lose 2 electrons, lose one here, and then lose another one, and it'll look like neon. So you can predict how many electrons an atom wants to gain or lose based on its position in the periodic table. Now let me just say that this method works really great for these atoms and for these atoms, but as you get farther away, especially in the middle, the atoms can do unpredictable things, so you can't predict so accurately what it wants to do when you're far away from the edges. But most of the chemistry we learn in the middle, in the beginning, is called the main group elements, and so we use it all the time. So we talked about combining a left plus a right atom. We called that an ionic compound, which forms an ionic bond because electrons are transferred, and now you know why they're transferred, because the element on the left wants to lose an electron, and an element on the right wants to gain the electron, so it's very easy for the electron to be transferred. And this forms some examples here, but they are not molecules. I'll tell you why in a second. And then we said when you had something on the right-hand side plus something from the right-hand side, it forms instead a molecule with what we call a molecular formula, with what we call a covalent bond, which is sharing electrons, not transferring, sharing. And here, of course, are some prototype examples. Now, we have a lot of basics out of the way. What I need to talk to you about is some special molecules that we come across all the time, and they are called diatomic molecules. Right? We mentioned oxygen. Oxygen does not like to exist by itself. If an oxygen atom, if it happened to be by itself, a neutral atom, and it bumps into another neutral atom of oxygen, like in space or something, and they just bump into each other, they're going to bond. They want to bond to each other. Why? We'll talk about it later. It has to do with how the electrons are arranged outside of the periphery of the oxygen atoms. We'll get to it later. But we just need to conquer and talk about the idea that there are certain atoms that just like to bond to themselves. Hydrogen does not exist by itself. Really, it almost always exists bonded to itself. 2 atoms of hydrogen bonded together, we call it H2. Oxygen likes to bond to itself. We call it O2. Nitrogen, we call it N2. It bonds to itself. Fluorine, F2, it bonds to itself. Chlorine, it bonds to itself. We call Cl2. Bromine, it bonds to itself. We call it Br2. And iodine bonds to itself. We call it I2. These are called the diatomic molecules. You're going to end up memorizing them without trying so hard because you're going to bump into it all the time. You'll never see a chemical reaction with just H by itself. It'll always be H2 if it's just a molecule of hydrogen, right? So in the periodic table, what are these? It's fluorine, chlorine, bromine, iodine. These are ones that are diatomic, and then you have oxygen and nitrogen and hydrogen. I believe that's 7. So 1, then 2, 3, 4, 5, 6, 7. There's 7 diatomic molecules. 1, 2, 3, 4, 5, 6, 7. These are the most common diatomic molecules you will find in nature. Notice that these noble gases like neon and helium, they don't bond. to each other. We said the noble gases don't like to bond to anything, even to themselves. So they stay as atoms. But there are certain molecules, like when you're in the hospital, you might hear, turn on the O2, doctor, whatever. That's because oxygen is a molecule. It doesn't exist as just an atom. I mean, you can rip it apart if you really wanted to do that, but it doesn't naturally exist by itself. It likes to bond to itself. So we call it an oxygen molecule. We call it a hydrogen molecule. We call it a chlorine molecule. We call it an iodine molecule, and so on and so forth. And again, these numbers down here, this is the number of atoms, 2 iodines, 2 bromines, and so on. All right. Now that we've talked about diatomic molecules that like to bond to themselves, I want to talk to you, I want to transition and talk a little more focused detail about the difference between molecules. Basically, we'll talk about molecules. And then we also are going to talk about sodium chloride as well. So let's talk about, which is an ionic compound that I kind of alluded to in the beginning. So what I want to do is I want to talk about molecular compounds. Another way to say this is just molecules. Now, because of the discussion, you should know what a molecule is. It's generally when two or more things on the right-hand side of the table try to combine. That is what we call a free-floating molecule. So let's talk about something that you may have heard of, and we'll write it by its proper name, methane. The chemical formula for methane, or the molecular formula for methane, is CH4. Now notice that this is, we can call it a chemical formula, we can call it a molecular formula because it's a molecule. But notice it tells you how many atoms of everything are present, but it doesn't tell you anything about the structure of what it looks like. And so that's something you have to get used to in the beginning. In chemistry, you don't always know what everything looks like because these formulas just tell you the atoms involved. They don't tell you the structure. So this tells you 1 atom of carbon and 4 atoms of hydrogen. But you don't know by looking at that. In fact, it looks like the carbon is on one end and the 4 hydrogens are all clustered together there. But that's not what methane looks like at all. When you look at a methane molecule, it looks like this. The carbon is actually in the center, and the hydrogens are equally spread around. If you notice the angle here between each of these hydrogens, the angles are all the same. And we'll talk about why. It's because when things bond, and generally everything likes to spread out and get as far away as it can. And so these are the maximum angles you can get surrounding a central atom like this. So this is called a ball and stick model. We use it a lot, especially in organic chemistry and also when we get to talking about the geometry of molecules. But this is a free-floating molecule. It's independent, and it is, you can bump into the container or whatever. Methane is a flammable fuel. It can be combusted. Why can it be combusted? Well, it's got a bunch of hydrogens attached. So when you burn it, the hydrogens pop off and combine with the oxygens, and you have combustion. Combustion is when things combine with oxygen. It's also rocket fuel. It's very flammable, very explosive, right? So it's a free-floating molecule. And of course, we already talked about our friend, famous water. It is also a molecule, right? Molecules, again, are things on the right-hand side of the periodic table that are bonding together. All right, what are some other examples of molecules or molecular formulas or molecular compounds, right? We already know about water, which is H2O, which we already said. This doesn't tell you anything. This is just the molecular formula. The ball and stick model can tell you what this might look like, and notice that water is a bent molecule. We talked about that before. We're going to explore a lot more detail later why these molecules have the shapes that they do. Then we have hydrogen peroxide. Right? Which is basically water with one more thing. So instead of H2O, it's H2O2. This means 2 atoms of hydrogen and 2 atoms of oxygen. But again, this doesn't tell you at all what it looks like. I'm going to show you what it looks like here in a few minutes. And then we have another example of a molecular compound, carbon dioxide. Right? Which is CO2. That means 1 atom of carbon and 2 atoms of oxygen. So basically, if the element does not have a number, then there's an implied 1, and that's how you read it. The numbers indicate the atoms that are there. Now, I've been dancing around the issue. Finally, I want to dot the I's and cross the T's and make sure we understand. We have illustrated 2 broad classes of bonding. We said that when 2 things on the right-hand side of the periodic table, 2 or more atoms on the right-hand side bond together, we called it A molecule. A molecule is a free-floating thing that's an independent thing that we have a molecular formula that tells us what atoms are there. For instance, for methane, it's CH4. For water, it's H2O. For hydrogen peroxide, it's H2O2, for instance. The bonding that's happening is called a covalent bond, which means electrons are shared. And so here are some examples. And then we said that was the right plus the right. But if instead we have something on the left plus the right, we said it's not a molecule. And I've been dancing around that. Now I want to put it to bed. We call it instead an ionic compound with something called an ionic bond. And instead of the electrons being shared, the electrons are being transferred from one atom to another. And so we have some salts. These are salts, sodium chloride. In fact, when you have something from the left combining with something from the right, in general, we call it a salt in chemistry. Sodium chloride, table salt, is just one kind of salt. Potassium chloride is also a salt. So what do these look like? If one atom of chlorine is not just bonded to one atom of sodium like a free-floating thing, what does it look like? Let me show you what it looks like. This is what it looks like here. This is not a molecule. This is a lattice, an arrangement of atoms which are locked into a grid structure. You can see that this looks totally different than a free-floating molecule. Methane is a molecule. It is electron sharing happening, and because of that, it is a free-floating containing unit that we call a molecule. It can bounce off the walls, it can exist as an independent thing like this. But when you really look at crystals of table salt, if you had a special microscope, what you would see is not free-floating units of, you would think the sodium and the chlorine would just be bonded together and they would just be able to float around. But actually, they're locked into a lattice like this, right? And that is common and pretty much universally common when you combine something from the left side of the table with something from the right side of the table. Why is it this way? Why does it not just form a molecule that floats around like that? Now, I could make you wait until we talk about ionic bonding further, but I think that that's kind of cheating you. Why don't we just contrast it now while it's in the forefront of our mind? The reason is because chlorine likes to gain an electron and sodium likes to lose an electron, then when you bring them together, the sodium atom will give its single atom to chlorine, right? So what you're going to have at the end of the day is the sodium is going to lose an electron, but remember the sodium atom was originally neutral. So when sodium gives an electron away, it's going to have more protons than electrons, and that means the overall atom is not neutral anymore. It's called an ion. An ion is a charged atom, either a positive ion or a negative ion, depending on if it lost or gained an electron. If a neutral atom loses an electron, the overall thing is positive, so the sodium atom becomes a sodium ion, and that's why there's a plus sign there. Its overall charge after it loses the electron is +1 because it lost an electron. Remember, the atom is neutral, so when it loses the electron, there are more protons left over, one more proton overall, so the charge is +1. And when the chlorine gains the electron, it only wants to gain one, remember, to be like a noble gas. And when it gains an extra electron, it was neutral, but now it has an extra electron. It now has a negative charge, -1. So what you have is now, after the electron transfer takes place, we have sodium, which is no longer what we call an atom. It's an ion, which is a charged atom. It has a charge, a +1. And then the chlorine, it accepted that extra electron, and it now has an overall charge of -1. So the sodium is positively charged, and the chlorine is negatively charged. Now, what have I been telling you since lesson number 1 is the most important thing, in my opinion, about chemistry, and that is everything is governed by the strength of the electric force. The electric force, one more time, is millions and millions and millions of times stronger than gravity. So if you just have neutral atoms, nothing is going to attract anything. But once the electron is transferred, and now that sodium is charged positive and chlorine is charged negative, these are charged objects. And charged opposites attract, opposite signs attract. And because the electric force is so strong, they are going to attract quite violently and stick together, right? Now you might say, well, great, then why don't we just have sodium and chlorine just stuck together by itself as a molecule that floats around? Why can't that happen? Well, it's because if I take a if I just had a bucket of sodium and I had a bucket of chlorine, which you can't really have a bucket because chlorine's a gas, but you get the idea. If I had a bunch of chlorine and a bunch of sodium and mixed it together, then all of the chlorine atoms are basically going to become negatively charged ions, and all of the sodium atoms are going to be charged positive and into positive sodium ions. So almost every single sodium ion is going to be a positive charge, and almost every single chlorine atom is going to be negatively charged into a negative ion. So you can't just have two of them stuck together free floating, because as soon as it bumps into its neighbor, it's going to stick to its neighbor. Because remember, every one of these blue objects has a negative charge, and every one of these red objects has a positive charge. So if these two stick together and these two stick together, that's fine, but as soon as they come close to each other, the blue is going to attract the red. And then this red is going to attract its nearest green neighbor, and the green neighbor is going to attract the nearest red neighbor, and so on. Because these atoms have overall charges, they're not going to be able to exist as just sodium and chlorine. It's like an independent free-floating unit, because as soon as a neighbor comes by, it's going to lock with it. That process will continue until they're all locked into a lattice. So that's why salt looks like a crystal. When you get up on it and you look at it and you shine a light and it looks kind of like a crystal, like shiny, that's because they're arranged in this crystal lattice. So when we say there's a difference between a molecule, which is a right plus a right, the electrons are not transferred. So you don't have ions, all the ion business happening. They're just sharing. So this is a nice stable configuration that can float around, and they're sharing and they're happy as an independent unit. But because the electrons are transferred between sodium and chlorine, and then each atom becomes a charged ion, and that happens to all the atoms present in your vessel, then they all stick together and they basically form a lattice, which we call a crystal, and that's why it looks crystalline like that. This process is going to happen every time you have something on the right-hand side of the table bonding with something on the left-hand, or I should say left-hand side of the table, right-hand side of the table, because that electron transfer always happens anytime you have left plus right. And so we're going to say that those are not molecules anymore, because molecules are free-floating kind of free-floating amalgamation of one or more atoms that can independently just kind of float around. But in sodium chloride, even though we write it as NaCl and KCl, these are not independent molecules that can just float around, because they're bonded to all their neighbors in a lattice. Now let me ask you this. It is true that one atom of sodium bonds with one atom of chlorine, but if I draw like a circle around this, I guess I'll just do it. Let me draw a circle around these two. Then I can say that one atom of sodium bonds with one atom of chlorine. But would it also be true for me to circle these four atoms right here, if I wanted to, and say, well, wait a minute, I have two green and two red, so that's like Na2Cl2, right? So I could say that NaCl was the formula for salt, but I could say that two atoms of sodium bond with two atoms of chlorine. And maybe this is the correct formula for that. But then I say, well, wait a minute, this is a three-dimensional thing, so I can actually circle these atoms right here. It's kind of hard for me to draw. I'm trying to circle four and then another four down below. I guess you can see it here, maybe 1, 2, 3. I'm trying to circle the 4 on top and then the 4 on the bottom, essentially. It's kind of hard to draw there. But you could call it Na4, Cl4, or you could call it, depending on what you circled, or you could call it Na8Cl8. You see the futility of this? Because they're locked into a lattice, what is the correct chemical formula for sodium chloride? Because I could say that 8 atoms of sodium bond with 8 atoms of chlorine in a lattice. Or I could say 16 atoms of sodium bond with 16 atoms of chlorine. Or I could say 100 atoms of sodium bond with 100 atoms of chlorine, because you see they're all in a lattice. So where do I draw the line? So when we have something on the left bonding with something from the right called an ionic bond, which is not a molecule, it's an ionic compound, that's what we call it, or a salt is another word for it. What we do is we don't choose any of these, we just choose the lowest ratio. And so even though it's true that 8 sodiums bond with 8 chlorines, or 100 sodiums with 100 chlorines, or 200 sodiums with 200 chlorines, what we really say is that the lowest ratio is 1 to 1, and it behaves like a fraction, because if you have 4 to 4, that's the same as 1 to 1. Or 8 to 8, that's the same as 1 to 1. Or 2 to 2 is the same as 1 to 1. So we say this is the quote-unquote chemical formula for sodium chloride, even though it's a bunch of things bonded together, it's the smallest ratio of sodiums to chlorine in this situation. Other situations might have, you know, 2 atoms of magnesium bonded to 1 atom of something else, and the ratio would be 2 to 1, but for sodium chloride, it's 1 to 1. We call this a formula unit. So here's something that you often don't quite understand when you first learn chemistry. When we write down molecules like O2, oxygen, H2O, water, H2O2, hydrogen peroxide, CH4, methane, these are actually the number of atoms in each of these molecules. Like literally, this is what it is if you could zoom in and look at it or make a model of it, okay? But for sodium chloride, since it's in a giant lattice, we just choose the smallest whole number ratio of the sodiums to the chlorines. We call it a formula unit. So we don't say that sodium is a molecule. We don't say that sodium chloride is a molecule. We don't say that sodium chloride has a molecular formula. We say that it has a formula unit. Formula unit is a word that just means lowest whole number ratio of atoms in the lattice. That's what it means. And so you cannot have one atom of sodium bonded to 1 atom of chlorine floating around and bumping in, and it doesn't work like that. Table salt is a solid. When it's not dissolved in water, of course, it's a solid, and it's crystalline because those atoms bond together in a gigantic lattice, the lowest whole number ratio being 1 to 1. We call it a formula unit for ionic compounds. So we call this a formula unit. I didn't want to write that first because then you would get confused. When it's a right atom plus a right atom, we call it a molecular formula because it's a molecule. When it's left plus right, we call it a formula unit, which is the lowest whole number ratio. All right. Now that we talked about that, there's one more thing before we close it out, and that is the difference between the molecular formula in general and the empirical formula. So, you know, you run into these terms, empirical formula, molecular formula. What does it mean? All right, well, the molecular formula, I'll just put a column over here for molecular formula, and empirical formula, I'll put it over here. In your book, you'll probably see, whatever book you're using, you'll probably see a definition. I don't want to write a definition. That's boring, and it also isn't very helpful. Let me just show you what it is. It's very, very simple. So let's take a look at hydrogen peroxide, H2O2. A molecular formula are the atoms and the subscripts that are literally inside the molecule. So hydrogen peroxide literally is a molecule of 2 atoms of hydrogen and 1 atom of oxygen. But if you didn't know that hydrogen peroxide looked like this, if you just did an experiment, you would know that there was basically a ratio, a lowest ratio of, instead of 2 hydrogens and 2 oxygens, the empirical formula is like taking the lowest ratio of this, and so the empirical formula would be HO. In other words, treat it like a fraction. 2 over 2, you know, you can divide top and bottom by whatever you want, so divide both by 2 and you'll get 1 and 1. So the empirical formula is the lowest whole number ratio of atoms that are present. Right? Let me give you another example and you'll see. Let's take a look at C2H4, which is a molecule we'll talk about later called ethylene, and it's got 2 atoms of carbon and 4 atoms of hydrogen. This is actually the number of atoms and the types of atoms actually in the molecule, but the smallest ratio would be if I divide both of these by 2, so it'd be CH2. Divide this by 2, you get 1. Divide this by 2, you get 2. Now this is not actually what the molecule looks like, but the ratio of the atoms are correctly present here. But the actual molecule is this. And then let me give you one more example. Famous water, H2O. This is the molecular formula. There's really 2 hydrogens and 1 oxygen. What's the empirical formula? Well, I can't really divide these by anything. Basically it's like a fraction that isn't able to be simplified, so the empirical formula is also H2O. Another example would be carbon monoxide, CO. I can't simplify it anymore, so the empirical formula is also CO. So you might say, why do we even have empirical formulas? Why would I ever use that? I want to know what's really in the atom. What's really in the molecule. I want to know what atoms are actually there. So why would I ever use an empirical formula, which is kind of lying to you? Here's why. Let's say you have an unknown substance, you have no idea what's in it, and you run experiments on it. And you run it through a mass spectrometer and other equipment to identify the atomic masses of the different elements that are there. Then you might ascertain, because you can figure out the percent of hydrogen and the percent of oxygen, and when you work out the math, you might realize that there's a ratio of a one-to-one ratio of hydrogen to oxygen. That could be the empirical formula. Or when you do the experiment, you might find that there's a ratio of 1 part carbon to 2 parts hydrogen. So this is what you call empirical formula. Empirical is a word that means it comes from experiment or it comes from observation. That's what empirical in this context really means. So if you do an experiment and you don't know ahead of time what it is, but you measure the ratios to be 2 parts hydrogen and 1 part carbon, this is empirical, but the actual molecule might be a multiple of this. So if, in this case, it's multiplied times 2. Double the amount of carbons, double the amount of hydrogens, right? In this case, it's also a multiple of 2. Double the amount of hydrogens, double the amount of oxygens. So when you're doing an experiment in the real world, you might come up with an empirical formula just because what your equipment measures is the relative ratios of the atoms. So you write down an empirical formula, but then you might then realize or understand that your molecular formula, the actual molecule, might be, or probably is, some whole number multiple of whatever you got for the empirical formula. So empirical formula, you measure it in a lab, but the molecular formula might be some whole number multiple of that. Or it might not be, because in the case of water, really there's no difference. Or you could say the multiple is 1. So there really is no difference between the two. All right. Now the last thing we need to talk about is I want to talk to you about different ways to represent molecules, right? Let's talk about something called a structural formula. Right? Well, first of all, we already talked about the molecular formula. So for water, we say it's H2O, right? And for hydrogen peroxide, we say it's H2O2. And for methane, we say it's CH4. But these are the chemical formulas. We call them the molecular formulas, but they don't tell you anything about what the molecule looks like. It doesn't convey anything about what the molecule looks like. So the structural formula would be something like this. Instead of just having H2O written in terms of the atoms that are there, the structural formula might show oxygen in the middle and bonded with the hydrogens that are there, and you can try to show some kind of angle because we know that water is a bent molecule. Hydrogen peroxide, what would that look like? Well, you're not expected to know this now, but it's an oxygen bonded to another oxygen, and then you're bonded to a hydrogen and bonded to a hydrogen there. Notice the molecule is not in a straight line, and also, you're just told H2O2. This did not tell you that the oxygens had to be bonded together. It could have been HOHO for all you know, but it's not. The oxygens are bonded together and the hydrogens are connected, but they're connected at weird angles. It's not in a straight line, right? And then for methane, again, you don't know how this is connected, but what it really looks like in terms of a structural formula is a carbon in the center and hydrogens on the perimeter and the periphery, right? But again, it doesn't really provide the whole story because it gives you a crude understanding of the angles involved with the atoms, but it doesn't give you any detailed information. This is just a structural formula to give you some understanding of what the molecule looks like. What you can do is you can write down the, this is called a structural formula, okay? And there are other ways to write down molecules here, right? So remember what methane actually looks like. Let me grab it. So even though we write it like this on paper, the actual methane molecule is the carbon in the center, the hydrogens all spread out. But notice that this looks quite different than what I drew on the board. This looks like a flat thing with hydrogens coming out, but the actual molecule doesn't look like that. This is just one way of representing it. To get a little bit closer to the actual shape here, I'm going to draw a line right here, and we'll try to draw it down below. It's not going to be perfect, but you'll get the idea. What you can do is draw the carbon in the center, and then what you can do is say, all right, I have one hydrogen coming up on the top. I have another hydrogen coming out at an angle like this. And what you need to do is somehow specify a hydrogen coming out of the board and a hydrogen going into the board. So the one coming out of the board is something like this. Draw a little triangle, and what you do is you shade this triangle like this, and a solid shading means that this hydrogen is popping out of the board. And then you have another hydrogen, which I'm going to mess this one up, but it's something like this. And you have another hydrogen right here. So this is this is probably not a great picture here. Let me erase this real quick and try to do a little bit better. Sorry about that. So this is more like this, probably something more like this. and the hydrogen, right here, right? And so you have this, when you have these alternating lines like this, it is, or this kind of shaded is what it is really. That is a hydrogen into the board, cocked into the board, and a solid shaded is popped out of the board like this. So when I go and grab the actual model, you can hold it up and sort of see a resemblance. You have one hydrogen coming up, you have one hydrogen kind of in the plane of the board. That's this one right here, and that's this one on the board right there. But then you have this one down here, which is coming out of the board, and then you have this one over there going into the board. So what you do is you say that these two are in the same plane. This one is this one, and this one is this one. This one coming out of the board is represented by the shaded wedge, and this one going into the board, this hydrogen going into the board is represented by the dashed. So anytime you see a drawing like that, it's called a perspective drawing. When you see a shaded triangle, it means whatever element it is coming out towards you, a solid, I should say a solid wedge triangle. And when you see a crosshatch triangle, it means it's kind of going into the board. It's crude because there's no way that you can draw an accurate representation of these models by just drawing them on a two-dimensional sheet of paper. For methane, it's understandable. For water, it's understandable. When you get to something more complex, it's almost impossible to visualize it by drawing it on paper. But we do try. Now, before I close out this lesson, I want to put a few other pictures up showing a little bit more about these ball and stick models, and also something else called a space-filling model of a molecule. So let me erase a little bit, and I'll put those up and we'll talk about them. Now you have to forgive me, I had to try a little bit better on this drawing. It was okay before, but this is a little bit better, I think. So what we have here is, again, methane, right? So these hydrogens are in the same plane. So that's like this one here and this one up here are in the same plane, and the carbon is in the center, right? We have one coming out of the board. That one's indicated by the triangle shaded or filled in wedge, and then the one going into the board is governed by the shaded wedge. So I just changed the angles on them a little bit. It's basically the same exact thing, but I just wanted to try my hand at doing a little bit better, as you can see that. All right, next we want to talk a little bit about these ball and stick models a little more, and I'll talk about water. So here's a ball and stick model for water. We've, of course, already picked it up and shows you many times that this is what it basically looks like. Water is a bent molecule. But we also have something called a space-filling model, which you will see. The ball and stick model separates the atoms so you can see the angles a little bit better. But in reality, these atoms are different sizes. Hydrogen is a very small atom, and oxygen is a much larger atom. It has more electrons, and so it extends farther out in space. So that's why this one's so much bigger. It still tries to show the correct angles, but it's difficult to see the angles on a space-filling model. But the space-filling model does show you the relative sizes of the atoms a little bit better, which can help you visualize how reactions might happen. So we use both of them. And so I might use this more to understand the angles, and I might use this more to understand the relative sizes of the atoms. All right, same thing I can say of methane down here. Methane, we've been putting up a lot here. This is my methane model, and you can see it looks more or less like what we have here. This is the ball and stick model. We have one going into the board here. And the space-filling model is very good for visualizing what it looks like. You can see that the carbon atom is bigger than these hydrogen atoms, and so it dominates the space. And the angles, it's tried to be represented, but it's just difficult to see what these angles are. When you look at something like this, it's hard to understand that the atoms are equal spaced at equal angles, whereas this is showing you very clearly the spacing of the atoms there, or the angle between them. So I actually prefer the ball and stick a lot, but when you're doing reactions and trying to visualize how they're going to happen, the space-filling model is very useful also. Two more quick examples. Here is hydrogen peroxide. I don't have a physical model for that one, but you can see hydrogen peroxide. Here you have the oxygens here, and you have the oxygens here, and you have the hydrogens on the end. But if you notice, if you look carefully at the perspective, this is kind of a twisted molecule. This one's going into the board, and this one's kind of coming off at a different angle. And so if you were to play around with this and rotate it, you would see that these are not all in the same plane. It's very difficult to see that in this model. It just looks like a blob, but you do see the relative sizes of the atoms a little bit better. And then finally, we have carbon dioxide, CO2. This one's a little bit different. That's why I saved it for last. The carbon is in the center, and then we have one oxygen flanking on either side, and we have the space-filling model showing that. Notice the relative sizes of these are a lot closer because the relative sizes of carbon to oxygen they're very close to each other because carbon and oxygen are close to each other on the periodic table. So the relative sizes of these atoms are very similar. Now, what is this business going on here? Well, it turns out in every other molecule I've shown you with a single line, this is called a single bond. These are each single bonds. These are each single bonds. This double thing is what we call a double bond. We're going to talk about bonding a lot later, so don't stress out about it. But when you see 2 bars, that's a double bond. Basically, it's the number of shared electrons. There's more electrons that are being shared. So whereas here is just a pair of electrons that are being shared, here you have more. And that's all I want to say about it now because I want to talk to you about it in a whole lot more detail later. All right, so what we're going to do for the very end of this lesson, how we're going to round it out. I'm going to erase this. I'm going to write down some molecules on the molecular formulas down, and we're going to count the number of atoms that we have, and then we'll call it a day. All right, now that we've talked about molecular formulas and ionic and covalent and all that, I want to do a couple of quick little problems. They're going to be very, very simple. Let's count the number of oxygens in the following compound here. So here we have aluminum, and then we have a parentheses. We'll talk about that in a second. And then we have another parentheses, and we have the numbers on the outside. So what this means is you have 2 aluminums bonded to 3 of this thing in parentheses, which we're going to talk about later. We're going to talk about it in its own lesson, but it's SO4. When you see something located in parentheses in a chemical formula, then whatever is in the parentheses is treated like its own little unit, okay? So what you have is this thing, we're going to talk about it and name it later. SO4 is kind of like its own self-contained thing, and there's 3 of them. 3 of these entities, which are bonded to 2 of these aluminums. So if there's 2 aluminums, and inside of this SO4, there's 1 sulfur and 4 oxygens, then how many total oxygens would there be? Well, if there's 3 of these entire units, and each unit has 4 of these oxygens, then you multiply 3 times 4 is 12. So you have 12 of them, 12 oxygens. All right, and that's all we want to talk about, oxygens. Right, so let's keep going. There's 2 aluminums in here. There's a total of 12 oxygens. How many sulfurs do you think there would be? Well, there's an implied 1 here. 1 times 3 is 3, so there's 3 sulfur atoms in this entire formula. All right, we're going to do 2 more just like that, and then we're going to say we're done. Let's count the number of hydrogens, hydrogen atoms, in the following. And it's kind of big. Let's look at it like this. NH4, parentheses 2, H, then we have phosphorus, then we have oxygen, we have 4 of those. All right, so all we want to count is the number of hydrogen atoms. All right, so again, when you see parentheses, this acts as a unit, and we're going to learn later that this is a unit that's kind of bonded together as a self-contained thing, and there's 2 of those, and then we have the rest as well. So if there's 2 of these units and each one has 4 hydrogens, and 2 times 4 is 8 hydrogens, and then we have 1 more hydrogen from the outside that's totally separate, so there's a total of 9 hydrogens. Right, in that situation. And just for giggles, let's complete the rest of it. How many phosphorus atoms do you see in here? Phosphorus, remember, is P. You can, if you're not sure about that, look at the periodic table and you can see that phosphorus is element P there. Well, there's only 1 phosphorus with an implied 1. And how many oxygens are here? Well, there's only 4 oxygens, so there's 4 oxygens. How many hydrogens? We already counted those. 8. 4 times 2 is 8. 1 more is 9. How many nitrogens? Well, there's an implied 1 here. 1 times 2 is 2. So there's only 2 nitrogens in this whole arrangement as well. All right, let's take a look at how many oxygens, atoms, in the following. So we have copper, Cu, we have a 3, we have OH, close the parentheses, 2, and then we have CO3, 2. Now at this point, it doesn't matter if you know what these things are, but what I am telling you is that you should know that anytime you see parentheses, it's a grouping, it's like an entity and we have 2 of them. This is a grouping, and we have 2 of them. So if we want to figure out how many oxygens total, we have 1 times 2. This makes 2 oxygens. And then 2 times 3 is 6. So we have 6 plus 2, and so there's a total of 8 oxygen atoms. All right, so let's finish the rest of it. How many coppers are in here? Remember, copper is Cu. Well, and if you're not sure, go back to the periodic table. Cu is copper. All right, how many are there? There's 3 copper atoms, okay. How many oxygens? We just said there's 1 times 2 is 2, so there's 2, and then 3 times 2 is 6, so 6 plus 2 is 8 oxygens. How many hydrogens? Well, there's an implied 1 here. 1 times 2 is 2, so there's 2 hydrogen atoms. There's nothing anywhere else. How many carbons? Well, there's none here, none here. There's carbon here, an implied 1. 1 times 2 is 2, so there's 2 carbons, and then we've counted everything. So in this lesson, we have covered an incredible amount of material, a lot of material. I don't like usually making lessons this long, but what happens is if I split it up too much, if I talk about molecules and then I talk about formula units and stuff, and then you never get the chance to compare and contrast them because they're not presented in the same place. You know, and then you don't, if I present, you know, what happens when you combine left plus right of the table and right plus right of the table, if you don't have them in the same lesson, you don't understand the differences because they're not presented together. So I try to make the lesson shorter, but sometimes they have to be longer. So we've talked about what happens when you combine things on the periodic table. We learned about 2 broad classes. When you have something on the left plus something on the right, we call that an ionic bond. That's an electron transfer from one atom to another, and then the resulting ions that are left over are attracted together, and they're bonded very, very strongly. Very strong bond because electric force of attraction is so strong, okay, between the positive and the negative ions. It's an ionic bond. We call it an ionic compound and so on. We also can call it a salt. Anything from the left plus the right, we call it a salt. All right. Then we said, in general, that's left plus right. You can also have situations when something on the right combines with something else on the right. Those are a different animal entirely. We call those molecules. So water is a molecule, carbon dioxide is a molecule, methane's a molecule, nitrogen dioxide's a molecule, hydrogen peroxide's, and there's lots of molecules, okay? But they're things that are on the right side, non-metals combining together. There is not electrons that are being transferred, they are simply being shared, and we'll talk about why they're being shared later on. But they're being shared, and so they're generally not as strong of a bond as the ionic bond because they're just being shared. They're not being transferred and so on. And we call that a molecule. It's a free-floating entity that is self-contained and can bounce and bump into other things, whereas the ionic bonds in the situations from before generally form a grid of, like we saw with sodium chloride, a grid of atoms that are all locked into place, into a crystal lattice, basically. So in one case, you got molecules that are separate things can float around. In the other case, you have a grid of salt, for instance, sodium and chlorine ions that are locked into place. Now, if you put that salt in water, the water can break it down and dissolve it. We're going to talk about that later. But in its solid form, of course, it's not a molecule, either in water or not in water. It's never a molecule. But the reason why is because of the way the bonding is different, okay? And then we talked about the different ways to represent chemical formulas. We said that we have molecular formulas, which are the actual number of atoms in the molecule. And then we have, for ionic compounds, like sodium chloride, we have what we call a formula unit. Because everything's in a giant grid, you really just need to express the smallest whole number ratio of the atoms. We call that a formula unit. But then getting back to molecules, there's all kinds of geometries that can happen. We've learned that water can be bent. We've seen that methane can form this other structure that's very interesting in three-dimensional space. So we have different ways of writing it down. We have structural formulas that we can write down on flat sheets of paper that sort of convey what they sort of look like, but not really. This is really not what methane looks like, but it gives you more information than this, which is the molecular formula. These are the structural formulas. And then, of course, you can write down a perspective drawing that tries to show you the atoms that are in the same plane, like these carbons and this carbon and these oxygens are in the same plane, but this one of the hydrogen is coming out of the board and this one is going into the board. It's attempting to show that. but it, in my opinion, is only really able to be, you can only really absorb it for simple molecules. You cannot, in my opinion, really visualize very well on a two-dimensional sheet of paper very complex molecules. This one, you can sort of get it with methane and water, but when you get very complex things, it's just hard to look at those wedges and understand it. But that is a very common way that we try to represent the molecular shapes on a two-dimensional sheet of paper. And then lastly, we wrote down some chemical formulas and we counted atoms. And we said sometimes we have parentheses and how to handle that, and what if you don't have parentheses, and so on. So this was a lot. I would love for you to watch this 2 times, maybe even 3 times. And then follow me on to the next lesson. We're going to continue working with studying molecules, counting atoms, and so on. And then when we're done with that, we're going to go talk a lot more detail about ionic compounds and how to name them and how to know what kind of compound they're going to form, and then also molecular or molecules and doing the same thing, how to name them. So this was the overview lesson, giving you the entire landscape. Then we're going to go in detail into each one of these little topics and get more practice. So if it isn't totally crystal clear at the end of this, just hang tight. We're going to do a lot more. So follow me on to the next lesson. We'll continue to build your skills.